Hi, everyone. Welcome to our first engineering mathematics session. I'm Liam, and I'm one of the senior design and analysis leads on our team. And I'm going to be responsible for giving all of us an introduction to what least squares linear regression is. So let's get right into it. This is the agenda for today's presentation. We're going to go over an introduction to what this regression method is and how it's relevant to our team. Afterwards, we're going to discuss what it means to linearize the data before performing the regression, which is a very important step because it makes the analysis very, very simple. Afterwards, we're going to consider two scenarios, one of which is called bivariate and the other is called multivariate. The bivariate scenario consists of two total variables, and the multivariate scenario consists of more than two variables. Both of these will be discussed later. Once that's done, we're going to go over some regression examples and look at a couple of cases that our team in the past has used some regression techniques to find some properties that we're interested in finding. And lastly, we're going to summarize what we've learned. So the introduction. What is least squares linear regression? In its most simple terms, it's a method that mathematicians, engineers, statisticians, or anybody who is interested in wondering how data relates with some other data, it's used to find a model to describe relationships between variables. So in the image on the right over here, this is an example of what you would expect to model data in engineering. This is taken from a transportation course. And you can see that on one of the axes, this is one variable. And on the other axis is another variable. And the idea is to find curves or lines that when you plot them in the data set, they represent the best fit for that data. And what do I mean by best fit? I mean that this model minimizes the squared error between what value the model predicts and what value we have as the data source. And the squares portion of least squares linear regression comes from precisely this. We can also use our regression model to interpolate or extrapolate some values. And interpolating means we basically use one of these curves to figure out what the most likely or most reasonable value is when we don't actually have a data point that corresponds to that. And extrapolation refers to basically extending the curve outwards in either direction and figuring out what data values occur there. Now we go to a small side note. Why do we want to square the error? This is a very interesting question, and there isn't really a precise answer that you can find online or in a textbook. But there are some points that many agree work well when we try to square the error. The first one is if we try to square the error, we can allow ourselves to find a function to minimize. And specifically, it's a well-defined function. What do I mean by well-defined? Well-defined means that whenever you square or create a function that's well-defined, let's say, it has the property that it exists for every real number, and it's also able to be differentiable, which means that you can find a rate of change for that particular function. And This is important because if we want to minimize something, we usually have to find the function's rate of change at a point. And afterwards, we need to set that to 0, which we'll see soon later in our presentation. The next one is squaring the error is often regarded as a common statistical method. It's been used extensively in the past, and there's plenty of documentation from various sources that say why it is used as it is in this context. And it's been the case ever since. It's the go-to method when we consider errors. And then lastly, one of the key points that is important in error analysis is that if we square the errors, it ensures that the total is non-negative. And this is helpful because it prevents trivial minimums from occurring. So we're always guaranteed that there's just going to be some minimum that we need to find. And that'll be evident when we go into our bivariate scenario. So how is this relevant to our seismic design team? There are 3 examples that I came up with, and I'm sure that most of the team who are in design and analysis are familiar with. The first one is free vibration testing, and specifically from that we can estimate the damping ratio. Next up is viscoelastic dampers, and this is an example where a force model is proposed for the damper, and that enables us to measure some of its internal material properties. And then lastly, material testing, specifically when we try to characterize balsa wood. So you'll see here that I have elastic modulus, and that is basically related to what the stiffness of the balsa wood is, or it acts as a measure of how resilient or resistant the balsa wood is towards being pulled or being compressed. And the images on the right correspond to each one of these 3 items. The first one is a free vibration test of roof displacement versus time. The next one is the viscoelastic damper setup. And this is an example of a 3-point bending test that is commonly used to find what this elastic modulus is. All right, so let's get into linearization. So you can see why do we want to linearize systems? The reason is, and I think the simplest reason is linear systems are always easier to analyze compared to nonlinear systems. And engineers and mathematicians, all of them really, really like solving linear systems because we know how to solve linear systems. Any nonlinear system is absolutely messy to solve. And in many cases, we actually require computers and numerical software to iteratively calculate a solution for them. And so in our case, if we can linearize the data, we're in a great position to do our regression. So how do we linearize our model? The first step is to propose a regression model. This can be any model. It can be linear. In that case, if you already have a linear model, you don't actually need to linearize it because it's already linear. But most regression models in science are nonlinear. And one of the common examples is an exponential function or a polynomial, something of that nature. To convert those nonlinear regressions into the linear form shown here, requires algebraic manipulation. And here's a quick example down below on how to do that. So in a hypothetical scenario, let's say that we had two different independent variables. So one of them is x and the other is y. V. X and v could represent anything you want. It's basically any variable that you have control over and can measure. A and b, these are unknown parameters that you want to solve. And regression is basically responsible for finding out what A and B are given X and V, and also Y. So in this case, you can see that obviously we're not in a linear form here because we have one of the variables inside the exponential function and the other one is being multiplied to that. So we got to separate them out. And to do that, we're lucky in this case because we can simply apply the natural logarithm to both sides. And based on what the logarithm does, if you have a product of terms, applying the natural logarithm to that separates each term out into a sum as follows. The next step is to simplify. And once you simplify that, you can deduce which variables need to be plotted. So in this case, we need the natural log of x squared to be plotted. And we also need the variable v squared to be plotted as well. And then the natural log of y is also supposed to be plotted. And so you'll see that this actually represents a surface in 3D because we have two inputs. One is x and the other is v, and both of them are functions. So you need 3 dimensions to fully visualize all of this. And in this case, what the regression surface will look like is going to be a plane in 3 dimensions. And having that plane allows us to figure out what the value of b and a are. And so that's an example of how to linearize data. So as I was saying, these are linearizations of common models. And the first one is the exponential regression. All you need to do is apply the natural log to both sides. And you'll see that you'll need to plot the natural log of y with respect to x to figure out what k and a are. The next regression is the power regression, and that is determined by applying the natural log to both sides yet again. Only this time the plotting is different. You're going to plot the natural log of y with respect to the natural log of x, and that will allow you to determine what b and a are. The last one is the polynomial regression. This is already in its linearized form. All you need to do is substitute x to the power of n as x sub 1 and x to the n minus 1 as x sub 2. And then you'll see that you'll have the case where you have some unknown parameter multiplied by one of the variables plus another unknown parameter multiplied by another one of the variables, and so on and so forth. And you'll see that this is that combination, that linear combination we were looking for. And as another note, some models can't be linearized. And in those cases, we're forced to use a numerical method to find what the unknowns are. In this session, we're just going to focus on the regression forms that we can linearize by hand. And we're going to see how to do that in the next session. In the next section. So now we arrive at the bivariate scenario, where we have 2 total variables. So right now I'm going to go through a derivation on how to arrive at the formulas for these. We have a linear model, so this is after we linearize the data, so our data should look like a straight line. And now the goal is to figure out how to find A and B. And to do that, I'm actually going to switch over to OneNote and going to start the derivation. So in our bivariate case, our regression model is y hat is equal to a times x sub I plus b. So a represents the slope of the line, and b represents the y-intercept of the line. The goal of least squares linear regression is to basically fit this line to a couple of different data points. So I'm going to, as an example, consider these red dots as our data points, and this green line as the line of best fit between them. The error between this line and each data point is going to be denoted by this length right over here. And this length has a value of y hat sub I minus y sub I, where y hat denotes the data value that the regression line predicts, and y sub I, that's the original measured data value. And the least squares part of this is we want to find what values A and B are such that the squared error is minimized, or the total squared error is minimized. And what this means mathematically is we want to figure out a function that involves A and B, and that's equivalent to the sum of all squared data points, or all squared errors. So it's going to be y hat sub I minus y sub I all squared. So this is summation notation. If you were to expand all of this out, you would get a sum of many different terms. And let's go ahead and substitute our expression for y hat here. So if we do that, we're going to get a times x sub I plus b minus y sub I all squared. And we can fully expand all of this, but actually I'll just do that right now. So as an example, so this would basically be a sub, not a sub, but a times x sub 1 plus b minus y sub 1 all squared plus a sub 2, not a sub 2, sorry, a multiplied by x times 2, I mean x sub 2 plus b minus y sub 2 all squared. And you do this on and on and on until you get to your last data point. So this summation right over here is basically summing what you see inside the sum, which is this squared expression, and you just add all of those expressions for I equals 1, I equals 2, all the way up to I equals n. And so let's continue going here. So we have this function, and this function, this actually looks like a surface in 3 dimensions. And what I mean by that is if you were to draw a 3-dimensional axis, the surface that this function describes would look something like this. And you can think of it as a cup, where it's kind of like the bottom half of of a sphere or some closed circular object. This looks like a valley, and in this case, I've drawn what looks to be a minimum point, which we'll actually see is the case for this function. So from that, if we want to figure out what the minimum of this is, we need to consider what are known as partial derivatives. So partial derivatives, they're like regular derivatives. All they do is they still measure the slope at some point in the function, but you'll notice that since our function has two different inputs, we're going to have two partial derivatives. And the way we denote partial derivatives is by this curly d symbol called partial, or in some cases you can call it a del. So we have partial f with respect to a. That's going to be equal to some expression. And then the next partial derivative is partial f with respect to b. And if you're wondering where I get these from, x1, x2, all the way up to x sub n, and their corresponding y values, these are all measured. So the only unknowns in our function come from a and b. And that makes sense because a and b are what we're trying to solve for. In calculus, which is a branch of mathematics, when you evaluate your partial derivatives of this function, that gives you a tool to figure out what the minimum of that function is. And so to do that, we're going to have to take the partial derivative of this summation right over here. And to do that, it's relatively easy because you can just apply the power rule from ordinary derivatives and the chain rule. And to do that, you're going to get 2 multiplied by a times x sub 1 plus b minus y sub 1 multiplied by the derivative of the inside with respect to a, which is just x sub 1. And then you have to add 2 multiplied by the next partial, well, actually not the next derivative step, which is basically the same thing. And I'm going to move it over here, move it over to the left so I have more space. And we're going to do that. Times x sub 2 and so on. So that's the partial derivative step. And for the partial derivative with respect to b, you basically do the same thing, but this time you're going to be considering changes only to b. And I should mention, this is only with respect to a. And to do that, you have to keep everything else constant. So the reason why you multiply by x sub 1 is because a is the only variable that's allowed to change. And b is, we're going to pretend that it's constant. And so in this case, we're going to let b change, but we're going to keep a constant. So what it looks like when we differentiate each expression is it's going to look like 2 multiplied by a times x sub 1 plus b minus y sub 1 multiplied by 1, which, because that's the derivative with respect to b of the inside function. So we don't actually have to show that because it's redundant. And this continues for the other expressions, all the way up to the nth data point. And so when we're at this step, we're basically at a position to figure out what the minimum is, almost, because we also have to make sure that this is indeed a minimum point. And to do that, we need to consider what the curvatures are at that point, because having your first partial derivatives figured out isn't enough to determine if it's the minimum or not, because the eventual goal is to set these partial derivatives to be equal to 0, and both of them have to be equal to 0. And this is not enough to guarantee a minimum point, because if you recall from calculus class, if you have some slope that's equal to 0 at a point, you can either have a maximum, as shown here, or you can have a minimum, as shown here. And the other case is in single variable calculus, if you have what's known as an inflection point. So right here, the slope, which is what these derivatives, these expressions give us, these are all 0 at these points. So there's actually no way to distinguish between what's a minimum and what's a maximum, or what's an inflection point. This gets more difficult in multivariable calculus, where you're dealing with multiple different dimensions. So to help us out with that, we had to consider these second partial derivatives. And to do that, all you need to do is differentiate each one again. So if I do the partial with respect to a of our first partial derivative, we're going to get our second partial derivative. And this is the notation for that. So if we go ahead and do this, and remember we're keeping a constant, we're going to see that it's basically 2x sub 1 multiplied by x sub 1, which is 2x sub 1 squared. And the next partial derivative is with respect to b, and so we're going to do the exact same step. So we got del squared f over del b squared, and this is going to be equal to, if we go back up to our original expression, it's going to be just 2. Or actually, hold on. It's going to be 2 plus 2 plus on and on and on. And the same thing with a squared, with the first partial derivative.
Liam, Grace has a question in the chat.
Oh yeah, sure. Yeah, go ahead, Grace.
I have a question. If you do partial derivative refer to a, why we multiply by x1 instead of a in the equation?
Oh,
never mind. I saw it's a squared.
That's okay. No worries. Yeah, partial derivatives is the trick is you want to keep track of which variable you keep constant and which one's actually allowed to change. Because in our example, if we're doing it with respect to a is the one that's allowed to change. Everything else looks like a constant. So yeah, that's the reason why we do it like this, and also because of the chain rule. There's a function in here that's being squared, so you first have to find the derivative of what something squared is, and then multiply by the derivative of the inside of that to get the derivative with respect to that inside variable. But no, that's a good question. It's something that I think I glossed over, so it's good that you brought that up again.
Thank you, Liam. Thank you, Koda.
All right, so let's keep on going then. So we figured out what these second partial derivatives are. I need to make a correction here because we have more than just one data point. It's actually going to be 2x sub 2 times x sub 2, and then that keeps on going. And the requirement for a minimum point, I'm going to draw it out again, is think of this as like a nice cup. The requirement is you want your function to be curving upwards. And you want your function to be curving upwards along the A direction and the B direction. And what calculus tells us is the condition that we need to satisfy in order for this to happen is the partial derivative or the second partial derivatives have to be greater than 0. Right, because mathematical convention says that if you have an upwards facing curve, that's called positive curvature because you can think of it as smiling. And contrary to that, if you have something that's curving downwards, it's negative, and that looks like a frowny face. So that's how I remember it. And if for some reason your second derivative is exactly equal to 0, that means something else entirely. And luckily, in our case, we set this up so that we're actually guaranteed a case where both our second partial derivatives in each direction is greater than 0. And so we're guaranteed a minimum. So we're happy about that. Awesome. So now all of that work was done to confirm that. The next step is to figure out what A and B actually are. And to do that, we need to go back to our first derivatives. So we go back to our first derivatives. Or I should say first partial derivatives. And you'll recall, I'm just going to scroll back up here. We have these long expressions. And for the convenience of fitting everything on the page, I'm going to narrow all of this down and condense it using summation notation. So you're going to see that right now. The first equation that we have is our partial derivative with respect to A. So this expression, while not particularly nasty, it's very repetitive, and that's why we're going to use sigma notation. So it's going to look like 2 times A multiplied by the sum of all squared x's plus 2 times B times the sum of all x's. And how I'm getting to this is I'm expanding all of these terms and collecting the like terms to rewrite as sigmas. And I'm just going to move this over on the other side because I'm going to be running out of space again. Maybe this part too. All right, so we're not finished with that one quite yet, but because we still have these y terms, and it's going to be minus 2 times the sum of yi, all the y's. And for minimums to occur, we need this derivative expression to be equal to 0. So we're going to set that equal to 0. And then similarly, we're going to have the partial derivative with respect to b. And that's going to be, it's going to look like 2 times a times x sub I plus 2 times b times the sum of 1, which is interesting. And we're going to basically just subtract off all of the 2 y's. Actually, hold on, I made a mistake. This is supposed to be x sub I times y sub I equals 0. And this is supposed to be y times I, just y. And the reason why it's xi times y sub I is because when we distribute, we end up having the x's multiplied with the y's, like such. And so we get that right over there. And so the moment of truth is the system that we get is 2 by 2, and it's called a square. And what this means is you can actually solve it. Solutions exist. And the solutions in a matrix form is, it's basically, let me just get rid of that. It's going to be the sum of x of I squared is 1 multiplied by a times b is equal to, we're going to, I should explain first. You'll see that 2 is common to everything. You can divide out 2 from each equation. That doesn't change anything. And after we do that, we're just going to move these yi terms to the right. So we get sum of that x sub I times y sub I and sum of yi. So at this point, we can actually solve this, and I'll make a note here. This expression, this actually simplifies to n because we have n data points, and if you add 1 n times, that's going to be n. So that's a nice simplification there. And this is the derivation for the system that you get. And you'll notice that it is a linear system. That's why we're able to represent it in this format. And solutions exist. And to solve for the solutions, you just need to multiply this left matrix by its inverse, or you can actually just use substitution or elimination, any method that you learned in linear algebra or any previous mathematical course that you've taken so far. But yeah, that's the bivariate derivation. So before I move on, does anybody have questions on how to get to this point? Oh wait, nobody seems to have any questions, so let's go back to the PowerPoint. All right, so from that derivation, you saw what we did. This is going to be a summary of that. So you'll see over here on the right, this is an actual, a nice image that was plotted in MATLAB. And you can very clearly see what I was trying to get at with the idea of a valley. Because A and B, these are 2 variables, and they exist in a 2-dimensional plane down here. The function that they output exists in a upper dimension, and so we need 3 dimensions to fully visualize it. Luckily, our world has 3 dimensions, so we're actually able to see what this looks like. And it looks very nice because you can clearly see that there's a minimum somewhere here. And you can see what I was also talking about regarding curvature, because you can see how there's a cup along one direction, and then there's another cup in the other direction. And that reinforces the fact that the curvatures are positive. So the function is basically smiling in both directions, which is pretty nice. And going back to that system of equations that we derived earlier, if you were to actually solve them, you would get these expressions. And these expressions, you don't need to memorize them or anything, because so many software, whether it's engineering or mathematics or statistics, will always have this built in. But the point of going through the derivation was to give you guys an understanding of how to actually arrive at this conclusion and understand what the computer is actually doing behind the scenes. And so anything else on this slide? The other important thing is making sure that the slopes are flat at the minimum. And you can imagine kind of balancing like a flat plane at the minimum point, because since it's flat in both directions, that corresponds to a flat plane in our visualization, which I don't have here because I wasn't able to figure out how to plot that as well as I should have. But if you imagine a rectangle that passes through and just touches the minimum point at that one spot, that's basically what the first partial derivatives are saying. This is a short little implementation in Excel you can use. If you ever want to create this regression calculator in Excel, it's fairly easy to do. You have your two columns of data. You count how many data values you have, which is n. You have to sum your x's, sum your y's, sum of your x squareds, and then sum the products. And these functions are what you can use to accomplish all of that. All right, so before we move on to the next scenario, we're going to quickly go over two measures that are commonly associated with bivariate scenarios. We're not going to go over this formula because we really don't worry too much about this coefficient. This is called the correlation coefficient, and all it does is measures the direction and strength of the trend of the data. What that means is it's basically saying how well is your fit, at least direction-wise. If it's perfect and it's positive, it means that if you change your variable, if you increase your variable, that results in an increase to the other. And positive slope means that. And the value 1 means that if your line passes through every single point perfectly, that means you have a perfect correlation. And you can see that the varying degrees of that. If your data is more scattered about, there's low correlation. And if your data goes in the other direction, it's called negative, because whenever you increase something by some amount, it causes a decrease to the other. And so that's where that idea of negative comes in. The coefficient that we're actually interested in is this one. It's called the determination coefficient. And it's basically measuring how well does our model capture the spread of the data. And the important thing to note here is that it is a single number, and it's between 0 and 1. And if it's 0, it means that our model is not very good. If it's 1, it means that our model is pretty good at representing what the original data is like. And so you'll see here on our example, R squared is given at 0.975, which is a really, really good fit. This means that it's capturing about 97.5% of the spread of the original data, which is very, very good, because it's essentially saying that our line is so good, in fact, that 97.5% of the time it's able to match what's given by the measured values. So in a sense, it is basically a grade or a rating of how well the model is. The formula used to calculate it is summing all of these squared errors. And you do that with the ones provided by your regression line and the original data values. And actually, this y bar represents the average of the y values. So yeah, the formula is basically comparing all of these errors with respect to the mean, which there's a whole discussion on why this is done this way. And there's too much documentation to go through in one session. So I just provided the formula here as a reference. And future links will be given to to help you guys understand more about that. But for now, we'll just say that it's a measure of how well our model fits the data. All right, so now we're going to move on to our multivariate scenario. So basically, the multivariable scenario is the extension of the bivariate scenario. That you have more than 2 total variables, and you can't exactly visualize everything as well as the bivariate case because, unfortunately, our world doesn't have 4 dimensions or 5 dimensions, spatial dimensions, that is. So we can't actually visualize what this looks like. We have to rely on what the math says. And the math says that the process that we used in the bivariate case carries over to the multivariable case. It's just that we're playing with more dimensions now. So there's that part. So the multivariable scenario is particularly hard to derive. And if we were to actually go through the derivation, it would take up a lot of time for our session. And this is meant to be an introduction to it. I've actually created a nice helpful document that will be sent out later to everybody who attended this session, and it'll go through a full derivation of how to get to this point. But the main takeaway here is all of the parameters can be solved using one simple equation. And this is a very, very ideal case in mathematics because rarely you ever get something as nice as this. Even though it doesn't look as nice when presented because there's a bunch of notation here. But what this is basically saying is the way to calculate your parameters, those unknown fudge factors, let's say, that you use in your regression, all of them come from matrix algebra. So this equation, this system over here, this is the system that you get when you go through the derivation. This is the second to last step before really finding out what these solutions are. And to do that, I will head on over to Excel real quick, and I'll show you how to implement this in Excel. So this is our multivariable case, and you'll see here that we have more than one variable, or more than 2 variables. Each one of these contributes something to the y value, and so I have a bunch of random y values here. But the idea is you take this grid or matrix of measured independent variables, and you want to rotate them around like this. So the transpose is a 90-degree rotation of this grid because you can see we have 0.429 here, 0.429 here. You have this value that goes down here. You have this value that goes down here. You have this one down here, and so on. So basically, transposing the matrix, this is part of the step that you do when you try to figure out what the parameters are. And if we continue on with that, you'll see that every single row in this grid is converted to a column. So you see that this row is converted to a column here, and it goes so on and so forth. So that's what the transpose does. And the next step after that is to multiply the transverse matrix by the original matrix. And to do that, you need to have knowledge of matrix multiplication. So the idea is to basically multiply this large grid that's been rotated 90 degrees by this matrix, the original matrix, And because of how matrix multiplication works, the resulting matrix is going to be a square matrix. There's an equal number of rows as there are columns. And this matrix is used to get to the system of linear equations that we see over here. And actually, yeah, here is the implementation in Excel. And if you want to do that, there's luckily a couple of functions you can use. There's the transpose function, which rotates this grid 90 degrees. That turns all of the rows to columns. There's also the inverse matrix function, which you can apply to that product of the transpose matrix multiplied by the original matrix to get a square matrix. And the matrix multiplication factor, that's also another function that's used to precisely multiply all of these grid values by these grid values. So with that in mind, does anybody have questions for the multivariate scenario? All right, I'll just move on then. So now we come to our regression examples. The first one is free vibration testing. The way that this equation is developed will be discussed in a future engineering mathematics session. But for now, all we want to focus on is this exponential term. This exponential term represents what's called the envelope of the response. And it's basically the outline of the peaks, as you can roughly see here. If we were to actually use least squares linear regression to get what the damping ratio is, we would have to figure out what the exponential function would be. And to do that, we need to propose our exponential regression. Once we figure out what B is, and I should add on to that, we first want to linearize this and then figure out what B is by using the regression method discussed earlier. We then have to figure out what this damping ratio is. So this curly symbol right over here is called zeta, and that's commonly used to denote what damping ratio is. And based on the regression format, it's the regression constant divided by this omega sub n, which you'll soon learn to be the natural frequency of that tower. And specifically, it's the undamped natural frequency of that tower. And what that means is it's the natural frequency of the structure if we assume that there's no damping that occurs whatsoever. And if we were able to actually measure this, we would be able to figure out a rough estimate for the damping ratio. So unfortunately, this isn't actually feasible. It's kind of impractical because in practice, we use another method called the logarithmic decrement. And the logarithmic decrement is much more efficient at calculating and providing the estimate for what the damping ratio is. But this is an example of what that would be like if we were to use an exponential regression. The next case where regression pops up is in damper testing. In some cases, the nature of the regression depends on what force model you use. And in this case, we've used our linear combination of displacement and velocity. And the unknown constants are stiffness, K, and damping coefficient, C, which need to be measured and determined. Now, the actual implementation of this model isn't, it's difficult because damper testing, as I'm sure most of you know, is particularly hard and difficult to not only set up, but to ensure that the results actually make sense. And because there's so much variability in damper testing, it's never the case that we're going to practically see linear regression on this type of force model. But in a case where most of the variables, most of the external variables are kept constant, it could be a possibility to perform a regression on this force model. And this would basically mean measure the force, displacement, and velocity at every point, and perform a least squares linear regression to find K and C. Practically, though, I'm pretty sure we rarely do that, or it's very, very hard to do that. And most of the time, we usually let the computer take care of all of it. And the last example is material testing. The assumption here is we use a linear elastic material. And for an axial tension test, you can see that the stress, sigma, is proportional to the strain, epsilon, this curly E. And capital E is precisely the Young's modulus, or the elastic modulus. This is only applicable in the linear region, so you can see basically in this example plot, 0 to where this is marked number 1, that's basically the linear range. And the idea is we would fit a line through all of those points, and the slope of that line gives us the elastic modulus. This is also the case in another test called the three-point bending test. And in this case, we're measuring force and stiffness. And you can also flip this around. You can also measure the displacement in response to changes in force. But the idea is the same. The slope, in this case, corresponds to stiffness, or actually, no, it is true. The slope corresponds to stiffness, but if we want to do a linear regression, we can figure out what Young's modulus is directly, or at least figure out a suitable estimate. And if we know what value E gives, that can be used to figure out what the stiffness is. So there's that. Very, very interesting mathematics going on, and very, very interesting topics to discuss in material testing later on. And so we've basically reached the end of the presentation. Just to recap, what did we learn? We learned basically why we're doing regression, or why it exists. And supporting that are some of the concepts that we discussed about. So linearizing data, bivariate, multivariate case. Coefficients, the only coefficient that we actually care about is R², and how to implement these in Excel. And we also looked at a couple of applications. And that wraps it up for today's session. Thank you very much.